Rates of reaction is where we're starting today, and this is our first lecture for this new unit covering chapters 18 and 19 in your book. So we need to define our reaction rate. Okay, and reaction rate it has two different definitions. There's two ways you can look at it. It is either the accumulation of product per unit time. Okay, also known as moles per second or moles per minute or something like that. It's just whatever, it's some kind of rate is what it needs. It's usually moles per second is usually what, how we calculate it. Or it is the consumption of reactant per unit time. Okay, again, moles per second or moles per minute or something like that. And we use these for two things. We use these okay, they're used to compare, when we have a reversible reaction, they're used to compare the rate of the forward reaction to the rate of the reverse reaction in order to determine equilibrium. Okay, so it's used to compare with the reverse reaction. Okay, or okay, it is used to compare itself. Used to rate. We compare it to itself. Okay, or I should say this. It's used to determine the effects of changing conditions. So if you increase the temperature, how does it affect the reaction rate? Does the reaction rate increase or decrease, and it goes to how many certain number of moles per second and that sort of thing. Or if we increase the concentration of one thing, how does it affect the reaction rate? Does it increase it? Does it slow it down? Those situations. Okay, so then what factors affect reaction rate? Okay, so what are the factors affecting reaction rate? Okay, temperature. Okay. Temperature will concentration. Okay, so we want to think about these in terms of molecules moving, right? So if we increase the temperature, that means we have more molecules moving around. They're moving faster, and they're going to hit each other more frequently and harder. Okay, if we have concentration, that means there's more molecules around. Okay, which means the chances of us having an effective collision are increased. What else do we have? What's that? Not necessarily volume, pressure. Okay. And the other one, which is relatively new, which we haven't really talked about yet until now, is the presence of a catalyst. Okay, the presence of a catalyst. These are the big four. Temperature, concentration, pressure, and the presence of a catalyst. Now, a presence of a catalyst will cause, it increases the rate, the speed of a reaction, the rate at which a reaction happens, okay, without actually getting used up by itself. We'll demonstrate that probably tomorrow, or no, we might get to it today. Okay, so it accelerates a reaction without getting used itself. I'm sorry, guys, I am having a bad handwriting day. Okay, so what things actually occur in a reaction? So what actually Okay, so what actually occurs in a reaction, or what has to happen in order for a reaction to happen? Okay, yes, there's some kind of a change. We are going to have okay, remember these guys? Okay, and this is moving that way. And then we get a different one. Okay, and that is moving this way. Okay, these two molecules, if they are sitting apart from each other, is it possible for them, are they just going to start lobbing atoms at each other in order to make a chemical reaction happen? No. What do they actually physically have to do in order to make new products? Okay, combine, kind of. They have to what? They actually have to run into each other. They must collide. Particles must collide to react. They have to. Okay? Not only that, but they also have to collide with enough energy so that they will actually exchange, they'll actually break bonds and rearrange them. So if we get a okay, and this collides with no, I need to make that closer. Yeah, let's make another one out here. Okay, these two molecules actually collide with each other. Right? This has to happen. Particles must collide to react. Now, not only do they have to collide, they have to do it with enough speed they have to collide with enough energy that will break the existing bonds of the reactants. So must collide with enough energy, nRg, to break existing bonds of the reactants. Okay. You guys following so far? All right, then when that happens, then you'll get okay, then you'll get a reaction and you'll have them going their own separate ways. And if you look really closely, we obeyed the law of conservation of mass. Okay. I changed colors going from this one to this one, but okay. So only then do we have enough collide for them to break the bonds of the reactants, and then the bonds reform. Okay, I'll just leave it at that. Then the bonds of the products reform. Okay, so we broke the bonds of the reactants when they collided, and then when they come back together, some of the energy gets absorbed to make new bonds. Okay, so they reform and they absorb the energy that came from breaking these bonds before. Now, that's the general idea. Okay, now we have an analogy for this, and we're going to call it the handshake analogy. And we're going to pause the video so I can explain it to you guys because I can't really do it on screen. So, we're going to hold off for a minute. Okay, so according to the handshake rule, we have to have two things occur. We have to, one, okay, we have the handshake rule. One, we must have sufficient energy. No weak handshakes. Our particles must collide with enough energy in order to break the bonds. One. Two, and I kind of drew it up here. These two molecules are colliding in a certain orientation, right? Can you guys see that? Yeah. Okay. So two okay, the molecules must have the correct orientation in order for the bonds to reform into the products. If the atoms aren't conveniently arranged, okay, you're not going to make the products right. And so it'll collide and it'll reform again without making your product. So these have names associated with them. Okay, this one must have sufficient energy. This is called the activation energy. That is the activation energy. The correct orientation is when it becomes the activated complex. Okay, and this is what you get when they collide with enough energy. Okay. All right. Okay, which brings us to a sample reaction. And we're going to call this part potential energy. Okay, potential energy diagrams. We have a fictional reaction going on. It is A plus B makes C plus D. Okay, we have two reactants and two products. And I want you to draw this graph. On this side, this is energy. On this side is the okay. And on the bottom is called the reaction coordinate, but it really just means that the reaction goes this way. Okay, that's as we move forward through the reaction goes this way. All right. We said earlier that, I think I said that earlier. The reactants, okay, the chemical bonds within the reactants have a certain amount of energy stored in them. Okay, and that amount, we're going to put it right there, and we're going to call it, okay, and it's equal to this value right here. And this is HF for the reactants. Okay, HF stands for is the heat of formation, okay, also known as the enthalpy okay, it is the enthalpy of A plus B, the total enthalpy of our reactants. That's the name of it. It's the heat of HF stands for heat of formation, and it stands for what's called the enthalpy. And it is just the energy stored in the chemical bonds of these reactants. Okay. All right. Our products also have an HF. They also have an enthalpy. And we're going to draw this one up here. So this is A plus B, and this one is C plus D. Okay, C plus D also has its own HF value, and it's up here. Okay, in this case, it's up here. And so it would be that, right? It would be this distance up to there. And so that would be the heat of formation. Heat of formation of the products. That make sense? Are you guys with me so far? Okay. This would be measured in kilojoules per mole. Okay, so think about it. That is the amount of energy that is stored in the bonds for every mole of that substance. Yeah? Kilojoules per mole. Okay. It's just the value. That is the energy value of this species. Okay. Now, we talked earlier that what two things had to happen for a reaction? Okay, they have to have enough what? Energy. And they have to collide with the right orientation. Right. So, and when they collide, they have to do so that what happens? Right. So we have to collide in order to break the existing bonds of the reactants. So that energy that they're going to collide with is like a hill that they have to climb. And this value right there, this value is called what? We've defined it. This is the amount of energy. It's the activation energy. It's not the complex yet. Okay, so this right here is the activation energy. This total height is it. So this is the amount of energy that is contained in the, what, Joseph? The activated complex, right. So right here, at that spot right there is the okay, and it's a very energetic construct, and it's a transition state between the A plus B turning into the C plus D. That is the activated complex, and there's a lot of energy stored there, so that when it continues, some of that energy is absorbed and becomes the energy stored in our products. You guys following here? Yeah, we're good? Okay. So what happens when we go through a reaction is that we get a difference between these two values. This height and this height has an energy difference there, right? Yeah? Okay, in math, we would call that delta HF. Here's HF of one, heat of formation of the other. This would be our change in our heat of formation, or our enthalpy change. And this equals I totally screwed that up. And I don't have any whiteout anymore. HF of our products minus HF of our reactants. Okay, which makes sense. It's our final minus our initial. It's our product minus our reactant. Now, let's think about this for a minute. I just thrown a whole lot of stuff at you guys. If we have a change between, this has a certain amount of energy in it. These guys actually have more energy stored in it, right? Where is that energy coming from? Now, catalysts don't supply energy. And we'll get to how a catalyst affects this probably on Friday. Okay, where does the energy come from to go from here up to here? Where do reactions usually happen? Inside what? Okay. The reactions we've seen so far happen in solution, right? That you mix them, you dissolve them in water and you let them react with each other because it allows for better mixing of the products of the reactants to make the products. Does that happen at absolute zero? No. Not quite. Well, if it's in a solution, that means it's a liquid. That means that there is some heat already present in the system, right? Okay, there's some ambient heat. The water itself is liquid, and so there's some heat that there's some heat just from being in the liquid. Reactions can absorb some of that heat from its surroundings to go from here to here. As long as we have enough activation energy, as long as there's a Kickstarter, as long as there's something that pushes it up the hill, okay, this reaction can go. And it can absorb some of the heat from its surroundings. Now, you guys have seen this before. What do we call a reaction that absorbs energy from its surroundings? It brings it in. So it would be endothermic. Oh, you guys remember that? Yeah. Endothermic. Okay, this is what an endothermic reaction looks like on an energy basis. If you start here and you wind up with more energy being stored in your bonds, it is an endothermic reaction. That means that if HF is greater than 0, it's an endothermic reaction. If our delta H is less than 0, then we have, what's the other one? Would be exothermic. Okay, so this HF goes from a lower energy state to a higher energy state. That would be an increase in energy, right? But this energy is absorbed. This is potential energy. This energy is stored in the bonds, which means it would have to come from somewhere into the reaction. That makes it endothermic. Uh-huh. Okay. What I would like you to do is on a graph right below it, okay, what would an exothermic reaction look like? All I want is the black line. You guys can label all the other stuff some other time. But I just want to see the black. I draw it in your notes. Okay, label it, then do it in pencil. Label it with energy and reaction coordinate, and show me what do you think the graph is going to look like. Okay, walked around and I saw a lot of you guys have these in the right spots. Okay, but since we still have to have an activation energy, we have to have an amount of energy that we have to overcome before we continue with our products. We'll label these. Okay, we still need to do this. We still have to overcome an amount. And so the graphs are similar. A and B and C and D are positioned opposite, but we still have the activation energy. And that means, okay, but this will give us a heat of formation that is less than 0 because we'd be going from here down to there, right? And that would be a negative heat of formation. Okay. Here's what an activation energy looks like. There's a match. Okay. This match is these guys. Okay. We know that there is energy stored in this match, and it is going to give off energy. It gives off heat, right? So it's an exothermic reaction. We know from experience that this is going to happen. So, as we go from here down to here, that energy has to We're going to be releasing energy. But is it reacting yet? No. What has to happen in order for it to get it to start reacting? Okay, we need to add a sufficient amount of energy to get the process started. Once it gets started, it's got plenty to keep going. Yeah? So, what do? We add some energy to it. Okay? Now, once it's going, it's got plenty of energy. All right, to continue itself. No. Okay, so does that make sense? What represented the activation energy? The striking of the match. The striking of the match provided this amount of energy to get over the hill for the reaction to continue. All right, so that's where we're going to stop for today is potential energy diagrams. There's more that we can cover here later, but we'll stop with that.